Okay, let's continue with part two of the proof of the safety of Gauss's method, which deals with rescaling any equation or row in a linear system, multiplying it by a non-zero constant. Okay, so here's the theorem. If a linear system is changed to another by swapping one row with another, that was the first case, or multiplying both sides of an equation by a non-zero constant, that's the present case. That's the one we're going to look at now. Then we're going to start with a similar goal to the first case. We aim to show that any solution of a linear system also solves the linear system produced by multiplying a row by a non-zero number. That's the row operation. Rho sub I equals k times rho sub I, with k any non-zero row number, and vice versa. That is that the second system has the same solutions as the first one. Okay, so here is our naming conventions for the linear system. We only need to have a special name for one row, E sub I. And again, this is an arbitrary choice, so our result will apply to any row. And we have M equations, N variables. And again, we have N's, a list or tuple of N values, which solve the system. And they solve the system exactly when substituting the values for the variables makes the following conjunction or logical AND of M propositions true. E1 of S is true, E2 of S is true. That is, S solves the first equation, S solves the second equation, S solves the ith equation, and S solves the last equation, E sub M. Okay, now if S solves, with a little misspelling there, EI of S, given by the following equation. EI of S is the linear combination on the left with i's and the di on the right. Then S also solves the rescaled equation E prime. Now if we look at this, let's look at the linear combination on the left. EI is starting with k times A1 times S1 plus k times A2 times S2 up through k times AN times SN, where I'm reading the second index, which labels the variables. And because that's just k times all the terms, I can factor out the k using the distributive property of numbers and get k times that linear combination shown, A1 times S1 plus A2 times S2 up to AN times SN. Now, because I can do this because k is not zero, and the previous equation shows that that linear combination is equal, has the same numerical value as d sub I. So I can replace the linear combination with the d sub I to get that this rescaled linear combination equals k times di. Well, that is just the rescaled equation. So if S solves the original equation, it solves the rescaled one. Okay, and we can turn this around and say if S solves the rescaled one, that's with the k's in it, then it also solves the original one. We can do this by, to do this, we multiply E prime, one with the k's in it, by 1 over k. We can do that because k is not zero, in order to cancel k in all the terms. And the result of that is just the original equation. This means that S solves the original system exactly when it solves the rescaled one. So here we have again an equivalence of the logical statement that S solves the original system is logically equivalent to the statement that S solves the rescaled system. Because all the other equations are the same. The only one that changes is E sub I. Well, let's translate this to sets. We can again write the original set as the set of all tuples such that that condition is true, because we can replace that condition with a logically equivalent condition with EI prime. We get that second form, and that second form is nothing but the definition of the solution set of the rescaled system. Now the proof patterns used here are essentially the same as in case one, with one slight addition. In order to prove an equivalence P is equivalent to Q, which is what we were doing in proving that this condition up here is logically equivalent to this, we showed that P implies Q. That is, if S solves this, if S makes this true, then S makes the following true. And then we showed it, turned it around and said, if S makes this true, then it shows this is true. Well, this is just appealing to the basic definition of logical equivalence. And that's it for this case.